SEP Challenges webinar. The focus of this webinar is to provide a brief overview of the SEP program as a whole, and then give room to each of the challenge leaders present in the agenda that you can see in the slide, present in greater detail their challenges, what they expect from applicants, and how they expect the submissions to be carried out.
Welcome, everyone. I am Ruth Sofria from the Fortis Research Institute in Munich, where I lead the Industrial IoT Competence field and I coordinate the CODECO project. In this talk, I will introduce CODECO and its vision for cognitive, decentralized edge cloud orchestration. In environments such as in industrial IoT, the applications that we use, for instance, for services such as predictive maintenance, are usually composed of several microservices. Normally, we containerize them for portability, isolation, and security, and then these containers are deployed. So the tools that manage the deployment and the runtime of the applications are, for instance, based on Kubernetes. So industrial IoT environments range from the so-called far edge, so close to the data sources, sensors and actuators, up until the cloud, where complex applications such as AI-based applications were usually stored and computed. And these environments are highly heterogeneous in terms of devices, in terms of protocols used and resources. So applications deployed are often require of be managed to ensure an adequate QoS answer or in terms of resilience levels. And as I explained, these applications are handled by tools such as Kubernetes, and Kubernetes was not originally developed for such heterogeneous environments. So CODECO is a set of tools that is currently available to extend Kubernetes, and as a framework, it aims to answer some challenges as the ones that I have mentioned. So in particular, high mobility, high portability, dense deployments, so environments with a dense number or a high number of sensors. So CODECO is a set of open source tools, and it is being developed in the context of the Horizon Europe CODECO project in support of a consortium involving 16 partners. And we expect to complete CODECO by March 2026. And currently you have already a set of tools that you can use, experimentation sets and applications. So the key difference of CODECO in comparison to plain Kubernetes is that it sees the industrial IoT, the IoT edge to cloud infrastructure based on 3 layers, data, compute, and network. CODECO considers that when an application is to be deployed, it should address the infrastructure as a whole, so seeing these 3 layers in an integrated way, and not just from a specific plane. So not just, for instance, from the network observability perspective, or from the computational perspective. So instead of managing resources at these layers in isolation, for instance, handling CPU and memory at the compute layer, or handling bandwidth and latency at the networking layer, CODECO orchestrates applications by jointly considering data computation and networking metrics. This enables resilience, energy-aware orchestration, a better decentralized control, and allows also for deploying these microservices across, for instance, multi-tenant environments. So CODECO as a framework integrates multiple modular tools, all open source. You have here a picture that explains from a level perspective how these components work together. The components can be used in CODECO as a whole, or they can be used in isolation. So the automated configuration management and security component, ACM, is the CODECO operator. It is the single point of access to the end user. Here, end user is a developer of applications or a manager of applications across the edge to cloud continuum. And ACM acts so in addition to being the entry point, it manages the application life cycles. The privacy, decentralized learning, and context awareness component, PDLC, provides intelligence with AI and metadata aggregation, and it is responsible for providing recommendations to a new scheduler that is integrated into the SWM scheduling and workload migration component. NetMA adds network awareness, so brings network observability to Kubernetes. It is also responsible for creating a secure overlay for the communication between the different containers, so the so-called pod abstractions in Kubernetes. And MDM handles data observability and status, and those metrics are brought into Kubernetes and helps us in having a better understanding of the resources across the infrastructure, the integrated infrastructure from the IoT edge or across the IoT edge to cloud continuum. A key difference from CODECO to plain Kubernetes is that it has support for deployment across federated environments, multi-tenant environments. So you have an example in this slide where basically what you see are different CODECO components, and as you can see here, they can be deployed across different regions, let's say cloud, far edge, or near edge, and they can also be run only on the edge. So CODECO is created so that it can be integrated just on edge-to-edge scenarios, edge-to-cloud scenarios, or far edge, near edge. It is also developed so that it can be run in constrained environments. So in addition to this framework, the project counts with different use cases that bring the CODECO orchestration to different domains. So you currently have several applications that you can download and play with on these different use cases. So the use cases cover different domains, for instance, smart cities, mobility, energy, manufacturing, and each use case demonstrates how CODECO can improve the application deployment or runtime in the different environments. So this can range, for instance, in the smart monitoring of the public infrastructure. You have an example of an application, sensing application, focused on, let's say, sensing the status of traffic management across different roads or cross sections in the city, and CODECO can help in orchestrating the computational power that is required to run these sensing applications, for instance. In the manufacturing use case, we use CODECO to improve the decentralization of mobile robotics applications. So I'm going just to enter very briefly to explain you very briefly about each of the CODECO components. There is, of course, more detailed information in our YouTube, also in our reports, in papers. But basically, so to give you an overview for the RCEP challenge, given that you are going to work with some of these components, in these slides you have a very brief overview of each component and also a QR code for the code of the component. So as explained, ACM is basically the first component that you see, is the main interface between the user and CODECO. It automates the configuration and deployment of applications. It brings monitoring at a computational level via Prometheus to Kubernetes, and also deploys and configures the full CODECO framework. So CODECO components, as I said, are modular by design. They can operate independently, and ACM can also operate, for instance, with other schedulers. So MDM brings metadata from different data sources, different, for instance, catalogs of data, and integrates it into a coherent graph model that can then be queried by other components in CODECO and assist in making orchestration decisions. For instance, some examples of metrics that MDM captures relate with age of information. That is a metric that is quite relevant for digital twin applications today, or freshness of data in databases, for instance. PDLC is the brain of CODECO in the sense that uses AI to provide, let's say, intelligent and profile sensitive orchestration information to the scheduler in CODECO that is inside SWM. PDLC reads monitor data that is collected by other components, specifically ACM, MDM, and NetMA, and then aggregates such data based on profiles that the user passes. For instance, the user says, I want the orchestration target profile to be resilience, or I want the target profile to be greenness, or both, and therefore PDLC handles recommendations in that context. So it creates costs for nodes that take into consideration what the user requested. It is composed of different components, as you saw in the former slide, and here I just give you an example on how PDLC computes greenness based on a target profile that was passed by the user. So that is passed in a, let's say, semantic abstraction of the application that we call CODECO application model CAM, and where, so it's a YAML file, there is a GUI also in ACM that you can use to create that YAML file that defines the application and its quality of service requirements and additional information. And for instance, the user can say, I want my target profile to be greenness, and therefore PDLC, in particular a subcomponent called context awareness, PDLC-CA, will use the information passed to, and also the information monitored to then compute so a cost for nodes and also for clusters based on greenness. So this can be as simple as greenness can mean, for instance, the energy consumed over time on nodes. It can also mean the energy consumed on nodes and on data transmission. It can have also other formulations. So in addition, so one part, of course, I said, of PDLC is aggregation and creation of metrics based on target profiles that the user selects, like resilience, greenness, and others. But there is also a component that is extremely important in PDLC, which is PDLC-DL, decentralized learning, which uses reinforcement learning for recommending allocation of the application workloads and eventually reallocation. So it uses autocritic methods and proximal policy optimization to recommend nodes to the scheduler for workload placement and to adapt to system performance changes. There is another component inside PDLC. This is an optional component, but very interesting, based on graph neural networks, which is used to predict future resource usage. So it currently relies on historical CPU and memory data, and then forecasts resource demand to minimize the overall cluster consumption and improve proactive orchestration decisions. The NetMA component is responsible for network awareness. So this is something quite new in Kubernetes. It provides network observability at an underlay and overlay level. And it also provides a secure overlay for Kubernetes, so between the pods and clusters. NetMA exposes relevant network metrics. I would call the attention for in addition to the regular metrics that we need in networking, such as bandwidth, latency, jitter, and others. NetMA also brings to Kubernetes energy, so an example of an energy metric that can be used at a link level and can also monitor other aspects such as congestion, etc. So the final component, extremely important, SWM, is the component that is responsible for scheduling and rescheduling of workloads based on the CODECO application model. The novelty is that it uses a graph-based deployment strategy to capture application requirements and end-to-end constraints. And it relies on a solver that aims to match these application requirements with the available compute, networking, and data resources, and therefore it moves beyond the regular filter and scoring approach from Kubernetes and makes it a more suitable candidate for more complex environments, such as occurs in federated environments.
Shifting now the focus to the STEP program, the Innovation and Research Community Engagement Program framework. What is the goal of ERSEP? The goal is to develop and expand the project's ecosystem. In order to do so, we invite multiple stakeholders, it can be students, SMEs, researchers, developers, to propose and develop extensions, applications of the CODECO framework. The ways that we can do this are multiple. And in this webinar, we are focusing in particular on the RCP challenges, but there's also been RCP in hackathons, in scientific events and conferences where people were awarded via their outstanding talks, presentations, and papers that were submitted. And the mechanism via which IRSEP basically awards these participants is via a monetary award, which is 2,200 euros for each awarded participant. The key, let's say, initiative behind IRSEP is the experimentation and validation challenges. These were designed to stimulate innovation, which we do by enabling external participants to carry out validation and experimentation activities within the CODECO framework. These challenges are proposed by the technical partners from the consortium. They are tailored with based on their activities in the project, so that we propose to the interested parties, like we said initially, SMEs, early developers, and researchers, something that is curated and tailored what the project consortium expects with the activities from CODECO. The challenges are open for application until the end of February 2026. And you can see now in this next slide the list of challenges that you can consult in the CODECO website. You go to the CODECO website, you click on the plus signal, and there's a drop-down menu where you can access a brief introduction on the challenge, and then have an additional button that takes you to the instructions on the GitLab, which is ultimately the platform that you're going to be using to submit your application. Speaking now of the application process, step one is always to read the terms and the conditions of each opportunity. So you are interested in a challenge, you should see the description of this challenge, see if, okay, I have sufficient knowledge in this area, it's a good opportunity for me, I apply. If not, you try to search for another challenge within the list that better fits your expertise. Step two is to fill the application form that you can find on the project website. This is a mandatory step that cannot be skipped. So, because if you do not fill in all the steps in this form, you cannot take part in the challenges. Once this application form is filled, the challenge leaders will receive the list periodically of the persons that have registered and will guide you towards submitting your findings on the GitLab. They will then, come February, evaluate the results, communicate to us at Innova who are worthy of being, say, awarded via IRSEP, and we will communicate those results to you and also finalize the process from an administrative standpoint. This is just a short overview of the application form. This is hosted on the EU survey platform, and it allows us at Innova to track the registrations via multiple fields that you need to fill. Just a brief note on the evaluation. The evaluation is composed of 3 fields: relevance, impact, and expertise. Each of these fields has a maximum grade of 5, so the maximum grade that you can have in the challenges is 15. This is to basically guide also and support the technical partners in their evaluation. They should assume that these key areas are fulfilled. So in theory, a good evaluation should have a good results in all of these areas, fulfilling the evaluation target that you can see. So relevance, it should be clear how the submission basically aligns with the core objectives of each challenge, impact, not just, let's say, speaking of the challenge individually, but also the long-term and potential outcomes of this submission from a future perspective, and expertise, obviously, if you feel the applicant really showcases the knowledge and the skill and the experience that they are basically showcasing in their submission. This evaluation will be conducted by the technical partners. Like we said previously, the results will be communicated to us. We will then finalize the process from an administrative standpoint, asking the awarded participants to fill a statement of discharge form. It's not a process that takes a long time, but it's just to ensure that we have all the information from a legal standpoint so that we can close everything and give you basically the award that you worked for.
Okay, so my name is Panagiotis Karamolegos, as we can see here on the slide as well. So I am from the University of Piraeus Research Center, and today I am here to present to you, okay, and discuss a little bit the IRCEP challenges of the first IRCEP challenge and the second IRCEP challenge, okay, that have to do with the CODECO data generator. So a little bit of an overview. So we have two challenges that have to do with the same, not the CODECO component, but CODECO asset, okay. So through CODECO we have created a synthetic data generator, basically an automatic tool that can generate synthetic data or random data, okay. So it's good to explain a little bit the difference between the two. Random data are just completely random data based on probabilistic distribution, okay. Synthetic data, from the other hand, is data that come from some random data, but also from realistic data as well. Okay, so one of the two architectures, as we can see here in the slide, the version 1 has synthetic data and the main version has just random data. So why are the synthetic data called synthetic? Because due to their nature or of being generated through random but also realistic, not realistic but actual real information, they seem to be realistic themselves, okay. So this is why we call them synthetic. It's basically random data but better, I will call them, okay. So we have two versions for this data generator. One of the challenges have to do with both, and the second challenge has to do only with the main version, which is the easiest to install as well. So what we're going to do today is we're going to have a look in the architectures of each one, explain a little bit how they work, but also describing what the challenges are and what we expect from the participants, and then having a look on the KPIs. And if we have time, I'm going to also be showcasing an example of how we can install the version 1 branch, okay, because it needs a little bit of some tricks in order to work, and the main branch is the easiest to install, so probably we will not be looking at this today. Okay, so let's begin with describing the challenges. So as said, there are two CODECO data generator challenges. The first one is, I'm going to read the slide here, okay? So this challenge focuses on enhancing the generation of synthetic data for Kubernetes custom resource definition schemas using CODECO's synthetic data generator. So as said previously, one of the two branches, the version 1 branch, provides synthetic data. Okay. But the main branch, the current branch, does not. It just provides data based on distribution, random data. So the goal is to improve CODECO synthetic data generator so that it produces synthetic data again, I will add here, okay, that closely reflects the structure and semantics of real CODECO CRDs. So basically the idea is to take the version 1 branch that produces synthetic data generator and use its techniques and methods into the version into the main version, okay, the main branch. And in that manner we create an updated CODECO synthetic data generator again that closely resembles the real metrics that we gather under CODECO for the 3 layers that we are working on. Okay, so the challenge objectives, so these are the objectives, not the KPIs. This is what we want the participant to achieve in the end, to be able to do. So first, to familiarize participants with CODECO's metrics. So these are metrics, as said, that have to do with data, networking, okay, users of applications of a CODECO cluster, of a Kubernetes cluster in the end, okay. So we want them to familiarize with these three layers of data. Produce synthetic data that accurately mirrors and structures and content of real CODECO CRDs. So as said, we currently in the main branch, what we have is just random data, but we would like to have them synthetic. Develop an improved version that integrates the synthetic data generation capabilities of the synthetic data generator v1 with the real CODECO CRDs provided by the main data generator. Okay, so this is what I said, the challenge. This is here where in the end we're going to be having a look on the KPIs of the challenge. Okay, so the participants are going to be providing this with some extra documentation, and this is what we expect as the answer of this challenge. And then submit a comprehensive set of results, including validation metrics and supporting evidence, demonstrating the fidelity and effectiveness of the enhanced synthetic data generation process. Okay, so this is also in collaboration with the previous bullet, what we expect as an answer, and this also has to do with the KPIs. Okay, so we need the information to be validated, we need supporting evidence, demonstrations, everything you can provide to showcase that yep, I have improved the main data generator, I have made it again synthetic, and this is my code and this is my documentation. Okay, good. So continuing to the CODECO data generator 2 challenge. So this is more of a comparison study, I will say. So let's go through the challenge. This challenge focuses on the evaluation and comparison of workload data generator tools against the main branch of the CODECO synthetic data generator. So as said, currently the main branch has to do with only random data, but there are other data generators out there that produce random data as well, and we would like to have a comparison study between the two. So participants, the 2 or the 3, okay, it does not matter. If you make a comparison study with more than one other data generator, this is even better. Okay, participants are expected to install, test and assess both CODECO's data generator and at least one comparable tool, delivering a comprehensive analysis of their respective strengths, weaknesses and limitations. Okay, it's as I said, basically a comparison study. So here we will be having a great look on the study, on its evidence, on the scripts used in order to provide the comparison. Okay, And we do not really want anyone to just go and say, the synthetic data generator here of CODECO, the main branch, is the best. We just need to actually provide, okay, our limitations in order to improve. So regarding the challenge objectives, we need to explore, the participants need to explore and install at least one workload data generation tool, okay, besides CODECO's we mean here. Deploy and test the CODECO synthetic data generator, this is the main branch. Perform a comparative analysis, as we said, between the tools. Identify strengths, weaknesses, and limitations. This goes for both solutions, as said, so we do need the weaknesses and limitations of our data generator as well. Provide evidence-based insights and recommendations for future improvements. This means scripts, diagrams, whatever you came up with that shows the strengths, weakness, and limitations, and next steps for the data generator. This is also viable for us. And in the end, of course, we do not expect here code. Okay, so for the CODECO data generator 1, we expected code, but the CODECO data generator 2, here we expect a PDF or a README with scripts, okay, on the repository that will be provided to you, or the repositories that you will be creating, okay, as an answer for this challenge. Good. So as said, we have two versions of this data generator. Let's have a look on both architectures here. So this is the branch v1.0.0, and this is, if we have time, what we're going to also be installing, okay, as an example. So this is also the synthetic branch, let's say. So what we have here, we have a Kubernetes cluster, and CODECO, the CODECO framework has three components that they generate data, okay, for these three layers through three components. So the first one is the ACM component, the MDM component, and the NetMa component. So ACM has to do with RAM, CPU, anything that has to do with the application that we're executing. MDM has to do with the data that we are using in the application, and NetMa has to do with the underlying network of the application throughout our cluster. Okay, so basically the generator here provides the data that these three components are providing, but because we cannot install them, okay, due to any limitations, we do not want to install CODECO, we just need the benchmarking data. For this kind of reasons, we install a synthetic data generator in order to provide this synthetic data to us like it was the actual CODECO executing behind. So all of these components have the same sub-architecture, let's say. So here we opened up only the ACM controller of the synthetic data generator in order to have a look how it works. The other two are working in the same way. So here we have on each controller two very important subcomponents. The one is the synthesizer and the other one is the collector. So the collector is basically a functionality that collects information from Prometheus. So what does this mean? It means that we collect real information of the cluster. So some of the information in the end is going to be real. Okay, so CPU, RAM, this is real information that comes from our cluster. And then we have the synthesizer. So the synthesizer takes the real information and some random information and tries to provide data based on the real and the random information together. So for some informations, for some data that we cannot really have a view through Prometheus, we are generating them. Okay, so in this manner, both of these subcomponents are in this controller, and we are providing some custom resources, they are called in CODECO. So basically objects that can be viewed and read by a user or another script through the Kubernetes cluster. And for each node, we provide one of these objects. So we can see here node 1 custom resource, node 2 custom resource. So this goes for as many nodes we have in the cluster. After than this, here we also provide a flow of how we can use the extractor script of the synthetic data generator. So both of these generators have an extractor script used in order to collect a data set of information. So basically we leave the generator running in the background, and we execute a script that will create for us a data.csv with all the information inside of it. Also, we have examples of this in our repositories under the CODECO Eclipse GitLab. So that's basically it. Okay, it's a pretty simple architecture, I will say. So let's have a look in the main branch. So the main branch is even simpler, okay, because we do not now have a synthetic functionality, we only have the random functionality. Again, we have the Kubernetes cluster, the 3 controllers. We can see that the MDM generation here, this controller, provides information through an API, not CRs, as previously due to the CODECO actual real MDM component providing information through an API server. Okay, so as you can see, we're trying to approach CODECO as much as we can, because this is our paradigm on how this synthetic information should be provided and will be provided in the real CODECO framework. So here we have the dummy controller. This is called a dummy controller because it provides dummy data, okay, no real data here. So even RAM, CPU here are through a probabilistic distribution, nothing else. We use again the custom resources definitions and provide this time only one CR with all the information of the nodes of our clusters inside of it. Again, we have an extractor script here below that collects all of this information that it is being executed in the background, and we create a data.csv again. We have an example of this in the GitLab repositories. Okay, good. So continuing, let's have a quick look on the KPIs. I will remind for the CODECO data generator 1, what we have here is the code that needs to be provided. Okay, the enhancement of the main branch with the techniques and methods of the version 1 branch. So in order to make results comparable and meaningful, the following KPIs are set. Okay, data fidelity. So we care about how correctly the synthetic datasets are reproduced. The content realism. So this has to do with the accuracy of generated values that your synthetic data generator produces. Here, of course, we do need evidence, okay, supporting your values. The generative performance, so how stressful is to the system your generation. The validation and robustness, so this is how many errors or failures your generator ends up, okay, while it is being executed. And the improvement over baseline. So this is the comparative performance of the main branch against your own synthetic data generator that you just produced. Okay. So these are the KPIs that we're going to be having a look. across the participants, across the answers provided by the participants. Continuing on the second CODECO Data Generator challenge, again to make results comparable and meaningful, the following KPIs are set. So the completeness of analysis, I will remind this has to do with a comparison study basically, okay. So this will be a readme with your scripts in a repository, for example, or a PDF, again with supporting scripts. So completeness of analysis is the first thing that we care about. Coverage of installation, execution steps, data quality, performance, everything that has to do with these type of generators. The depth of evaluation, this means the level of detail describing strengths, weaknesses and limitations, because as said, this is very important for us. This is why this challenge exists. Evidence and validation. So this have to do with what was your quantitative and qualitative evidence and results and methods. Okay, we need you to explain this in detail. Then we have the clarity and structure, so this has to do with the organization and readability of your report. Okay, we need your report to be able to be read and understood by us in order to actually know that what you're saying does make sense. And then we have the actionable recommendations. Okay, actionable recommendations, this has to do with you providing the next steps on how would we make this a state-of-the-art synthetic data generator. Okay, the two challenges, because I would like to fit in some time to install at least one of the versions here. So here you can see the instruction repositories for each challenge. Okay, so for each challenge we have this quick start section, and it's something that each participant, I will believe that they should go through. Okay, so for the challenge 1, for example, we have go to the two readmes of each CODECO synthetic data generator version and make an installation. Okay, so if we go here, we click this, we can see here, I have it already open here. It provides us the steps on how to install each version, and this is important for you because you need to install them. Okay, so let's try to explain an installation of one of the versions. So this is the version 1, the synthetic data generator actually, okay, the one that all actually provides synthetic data. So what I have here is I have a repository, the v1, and I will go inside. So here, okay, I am basically inside this folder, and the very important thing is currently what I have is a kind cluster, okay, with the nodes kind control plane, kind worker, and kind worker 2. You have to go in this netmac controller deployment YAML under the netmac controller directory and basically provide your cluster, okay, because this was different. If we have a look here, here the second worker was missing, and as you can see, the adjacency matrix is different because the example here provided has 2 nodes only, so we changed it to 3. So okay, as you can see here, the cluster is basically just a core cluster, nothing installed really. And we will go through the readme over here, and we will basically make the installation. So I have already cloned Prometheus, so this is it, and then I'm going to apply the manifests, and actually I've done this before our call here, so probably this will not take too much time. Okay, so I can see stuff are beginning to running, pod initializing, that's good. So basically now we are installing Prometheus. Prometheus is a monitoring component, okay, that provides free monitoring to our cluster, okay, basically collecting all the information such as RAM, CPU, bandwidth information, packet losses, etc. I have already done this step as I've shown, basically changing the adjacency matrix and providing my nodes, and I am ready to apply my controllers when Prometheus is installed. Prometheus is done, so Prometheus is being installed under the namespace monitoring, and I can see everything is running. And now here, as we can see, we have this apply controllers script, okay, this bash script, and we're going to execute it. So after executing, we can say it will need some time. Let's give it some time. So we had a crash loop back off, but this is okay. Probably we get one or two crashes due to Prometheus still spinning up, but because we do not have a lot of time, okay, let's try to collect some information. So let's try to collect information of the ACM of one of the controllers here. So here we just need to change the name of one of our nodes, and here, as we can see, what we've done is we requested let's see, we requested CPU, we requested memory, how many node failures were there, and the node energy, the node security, okay, and we can see the node security was randomly set to low. We do not have any node failures as I've seen. Okay, so here this is the first value, this is the second value, okay, this is the third value, this is the node failure. Probably we had a node failure at some point, etc. So this information that we are looking here is a little bit, you know, all of it congested, but this does not mean that we just look at this and we're saying, okay, we have the data extractor as well, and as we can see here, we have an example of these kind of values all together for you as well, okay. So have a look at this, try to execute the extractor script in order for you to collect your data. Okay, that's it. You've seen the installation is pretty easy, okay. In both versions it's pretty easy, so I really do suggest the participants to do this. I believe both of the challenges are pretty nice, okay, and very interesting to do. Good. So
I think you can see my presentation now. Yes. Okay. So, hi everyone. My name is Risk. I'm the research lead of distributed data architectures at the ITCAT Foundation, and we're organizing a couple of the IRSF challenges within CODECO. In particular, the challenges that we are organizing are focused on the intelligent recommender, which is part of the PDLC component of CODECO, and the objective of this component in a very summarized way is to provide intelligent recommendations on where to allocate tasks or applications across different nodes in a Kubernetes cluster to optimize a specific objective. The core of this intelligent recommender is based on a reinforcement learning model that is pre-trained to work on a specific objective, for example, energy consumption, or if you want to improve the load balancing, or a custom metric that the user defines, and then based on after a phase of training, the recommender starts generating recommendations that fit with the objective that was identified. The challenges that we have on the intelligent recommender are focused on improving the scalability, generalization, and the usability of the recommender. And in particular, we have two challenges. The first of the challenges is aimed to test our intelligent recommender with the objective of achieving an ideal or an optimized load balancing between the nodes that we have in the cluster. And with this challenge, we want to test the generalization capabilities of the intelligent recommender, because the model that we have right now is not trained to optimize load balancing, but rather is trained to optimize energy consumption and the resilience of the system overall. So the objectives of this challenge is to model the load balancing problem based on the metrics that are being collected. We expect participants here to do a conceptual exercise of understanding what metrics that are collected by the system are needed to model this load balancing problem. Then the second objective would be to train or fine-tune the reinforcement learning model that we have to optimize this load balancing objective. And the final objective is to evaluate the optimized allocation, running a series of experiments and validation to make sure that the solution that was provided is actually coherent and makes sense for the optimization of the load balancing. The components that will be used in the challenge are Minikube as a Kubernetes test environment, the online reinforcement learning framework, which is the core part of the intelligent recommender of CODECO, and then two custom components, the Kubernetes operator and the pod generator, which are used to generate simulated workloads and to allocate them based on the recommendations that are provided by the intelligent recommender. The expected outcomes of this challenge are for the participants to familiarize themselves with the online RL framework of CODECO and to be able to deploy it and understand its inner working, to understand and know how a reinforcement learning model can actually be used to optimize the load balancing of a cluster, and to demonstrate with quantitative results that the provided solution actually fulfills the stated objectives. So how are we going to evaluate the solutions? What technical KPIs are we going to use? And here we have 3 KPIs identified. The first one evaluates the problem solution. So we expect people, participants, to use at least 2 metrics collected by Prometheus in the modeling of the load balancing problem. The second one is about the created reinforcement learning solution itself. And here we will evaluate the average award per epoch of training in order to see how long the model takes to converge, for example, and other technical aspects of the model training process. And finally, the third KPI is evaluating the generated recommendations themselves. And here we will be looking at measuring the percentage of improvement in the load balancing based on the modeling that was created over the bare bones Kubernetes scheduler. So this was the first challenge. Now, the second challenge is focused on benchmarking the CODECO Intelligent Recommender across diverse vertical workloads. And what we aim to do here with this challenge is to evaluate the applicability and adaptability of our Intelligent Recommender in different scenarios. We want to see if our Intelligent Recommender works well with different types of applications. For instance, shorter applications that require very high resources, or longer applications that are more dormant, that don't require a lot of resources. And specifically, we want to focus on how our intelligent recommender works in different verticals or different sectors. Apologies, sorry. So for this challenge, our objectives is we have two main objectives. The first one is for the participants to analyze the edge cloud applications, the characteristics and specifications of edge cloud applications across at least two verticals. For example, they can be mobility or healthcare, industrial IoT, any two verticals that are of interest to the participants and that are obviously related to the edge cloud continuum. So we want participants to analyze and understand what type of applications, what characteristics these applications have, and how they can be modeled based on a set of resources. So how much CPU do they usually require? What type of range of duration they can be expected to execute for. And then the second objective is to evaluate the quality and accuracy of the reinforcement learning of the intelligent recommender, let's say recommendations in these different scenarios. We want to see if our intelligent recommender works equally well with different verticals, or if it underperforms under specific circumstances. So the components that will be used are the same as for the first challenge. We have Minikube as a Kubernetes test environment, the online RL framework as the core of the intelligent recommender of CODECO, and then the I2CAT Kubernetes operator and the I2CAT pod generator, which will be used as complementary components in order to perform the evaluation of the intelligent recommender. So the outcomes of this, the expected outcomes of this challenge are very similar. We expect people to understand how the online RL framework works, how to deploy it, get familiar with it. We want participants also to analyze and propose a set of comprehensive workloads representing different verticals. Again, understanding what type of characteristics these different verticals usually require. And then finally, demonstrate the impact of this variation of the characteristics on the recommendations of the intelligent recommender. That's for the KPIs that will be used to evaluate the solutions of this challenge. We will have an KPI measuring the quality of the solutions in representing the workloads of at least two verticals. And then we will have 3 KPIs that will measure the impact of the actual recommendations on the energy consumption of the overall cluster. So we will measure the total energy consumption, the energy consumption per pod, and the number of running pods to make sure that this energy consumption or any potential improvement of the energy consumption doesn't come at the cost of running fewer applications. That's all from our side, I think. Thank you and good luck.
Hello, my name is Ruth Sofia. I'm affiliated with the Fortis Research Institute in Munich, and I am the coordinator of the CODECO project. I would like to welcome you to the CODECO Innovation and Research Community Engagement Program Challenge on Energy Awareness Strategies. The goal of this challenge is to bring energy awareness into the process of deploying applications across the edge-to-cloud continuum. So in this challenge, you will use built-in CODECO functions and also functions that you create to test and to evaluate how these functions can impact the scheduling, can make the scheduling more energy efficient. Your task is to improve the greenness of the application deployment by defining and validating new types of greenness function. So you have one example on this slide, which basically we name greenness to a product between the node energy, so the energy consumed in a device, and also link energy, the energy consumed during data transmission. So the idea is that you will create and check, also compare functions that are already available, and then analyze, visualize their impact. So you can use tools such as Prometheus and Grafana to see the results that you obtain. We hope that you can also provide a comparison on the different functions. So in this figure, you have, let's say, a simplified version of CODECO. CODECO is composed of a set of modular components. You have as first component ACM. ACM is the CODECO operator and basically sets up all the other CODECO components. So CODECO distinguishes two main user roles, the application developer and the cluster manager. And so as you see here, all the logic goes via ACM. So highlighted in this slide, you have the components that are expected to be used, or the main component that is expected to be used in this challenge, PDLC, which means privacy, decentralized learning, and context awareness, and in particular a subcomponent called PDLC CA, so context awareness, which is the component that is responsible for generating these costs, node costs, so greenness. So as you see, PDLCCA reads information about, let's say, metrics that are provided by ACM, also by other components, such as MDM, which provides system and data observability. So what you have here and what is being highlighted in these slides are the interfaces to the different components. So for instance, that from MDM, there are metrics coming that relate with data. From ACM, metrics that are come and that give status at a computational level, for instance, CPU, memory, and other metrics. So the output of PDLCCA, so these greenness costs that you are going to play with, and also additional recommendations about node costs, for instance, how nodes are behaving in terms of CPU or memory, are provided by PDLC so inside PDLC to a decentralized learning module, PDLC DL, which is based on reinforced learning. And then there are recommendations given to the component that handles the deployment of the application, so SWM, the seamless workload migration, which contains a new Kubernetes scheduler. So in these challenges, I have explained the focus is on PDLCCA. The subcomponent computes aggregated costs or composite costs based on profiles that the user defines. So for instance, the user, when deploying the application, says, I want to play with greenness. So I want to deploy my application and I want to have into consideration what is the cost, the energy cost, consumption cost of each node. So your task is to experiment with some functions that we provide already to understand how it works, and also you have also the opportunity to improve those metrics. So you can use metrics that are observed in CODECO, CPU usage, node energy consumption, link energy consumption, and you can also propose others. So for instance, CODECO can monitor, or you can create a user-defined function that monitors, for instance, CO2. We have some examples for that as well. So in this example, simple example is what I have been explaining. It's about greenness and how greenness can be computed as just a product of the consumption of energy at a node level, so computational level, and also at a networking level. So you have here the basic example of what PDLC-CA does. So it basically computes the aggregated metrics, then stores them, passes them to another subcomponent in PDLC, so PDLC-DL, but can also pass it to a scheduler. And in the case of this challenge, it will pass it directly to the scheduler. So with which components are you going to play with? While you can install the full CODECO framework, and we advise so that you can also understand a little bit how it works. In fact, for this challenge, you just need a subset of components. So PDLCCA, as I said, the scheduler, NetMA, in particular the monitoring part, which relates with observing energy at a network level, and ACM. So there are some components that you can bypass. There are instructions on how you can deploy the full CODECO framework or how you can deploy each of the components. So in this example that you see here, you have a simple cluster composed of a control node, so a laptop running different tools, and then there are 3 Kubernetes worker nodes, so in this example represented as embedded devices, and so CODECO monitors some metrics on each of these worker nodes, and also so these greenness costs and also other costs are computed having all this in mind. So specifically focusing on energy, what we use is for node energy we monitor energy consumption based on the Kepler plugin. So it's the Prometheus plugin that uses eBPF to monitor CPU performance counters and then to generate the consumed power. And so there are some challenges with Kepler, of course, but it's also interesting to use, and it's basically quite used in these environments. At a networking level, we also use eBPF, but we use other counters and other aspects from the hardware to bring energy information to CODECO. So there are some. So you have here just an example on what the PDLCCA monitors and then gives. Okay, so here is you can see some data, and then there is a CSV file that is generated with all the data that we collect. And so for instance, here you have a list of worker nodes and then the metrics, the energy metrics that are being collected. So I thank you for your time. In the CODECO Eclipse GitLab, you find all instructions and all contacts, and hope that you enjoy the challenge. Thank you.
Okay, so hello everyone. My name is George Koukis, and I'm from the Athena Research Center and the Demokritos University of Thrace in Greece. Today we'll present you the CODECO RCEP challenges that focus on CODEF, the CODECO experimentation framework, and benchmarking. The challenges are part of the CODECO project and the RCEP program and aim to engage the community in hands-on experimentation, evaluation with CODECO through benchmarking, and testing. Also provide solutions and suggestions for the next phase of CODECO and CODEF. So participation in this challenge follow a simple process. I will skip this for now to keep it simple, but you can check the details and steps from for registration by yourself. There is also a QR code you can check in order to get more details about the registration process. So as explained, the RCEP challenges are open experimentation challenges addressed to students, researchers, developers, and practitioners. So here we have 3 CODEF benchmarking challenges. The first one focuses on specifically on CODECO, executing experiments and testing things with CODECO. So we can get insights on the results and limitations. The second challenge is about providing security solutions, which is critical for any cloud edge framework. And the third one focuses on quality of experience and quality of life for developers or experimenters with the aid of AI. This challenges address, let's say, the need for robust, scalable, and secure deployments, with the goal being to evaluate the trustworthiness of CODECO and CODEF, evaluating performance under load, having security under attacks, and reliability during development and operations. So the challenge is also to highlight the use of modern techniques, including benchmarking, advanced testing, debugging, and AI assistance. Of course, there's a financial reward probably you already know it. Award for the best solution for its challenge, with winners announced in the RCEP page and CODECO page. The goal is for the successful ideas and solutions you provide to be integrated, utilized, and mentioned in the CODEF main repository, so external users and experimenters can use them, execute them, and also provide enhancements for the CODECO experimentation framework and CODEF as well. CODECO as well. So each challenge has its own GitLab repository with detailed instructions, example setups. You can check it here under the GitLab repository, the CODECO repository in GitLab. And let's move to the challenges one by one in order to get more details. The first one, first of all, on your left side, you can see there's a QR you can scan in order to go directly to the GitLab link and familiarize with the repository. The first challenge focuses on CODEF, on the dynamic stress testing and benchmarking of CODECO. So participants here are asked to define realistic stress test scenarios that include, for instance, high load, concurrency, resource exhaustion, network failures, etc. And when we're talking about dynamic stress testing, we're not talking about a single static load test. What we expect is to have scenarios where we have load, resource pressure that changes over time in order to see how an environment with CODECO installed responds to different conditions, real or synthetic, or how an application runs that runs with CODECO runs compared to a baseline, for instance, vanilla Kubernetes or a different Kubernetes distribution. After executing the experiments, you must then collect and store metrics in a database that you will create, not just the logs, but a structured performance data evaluation. For instance, some metrics you might want to use are for networking, latency, throughput, or network usage, for resource utilization, CPU, memory, for nodes or containers used, and the system behavior, for instance, stability over time, failure recovery, etc. And again, the goal is to identify bottlenecks, provide data-driven feedback that can improve CODECO's robustness and scalability. In all experiments, but in the first challenge as well, a critical requirement is automation. So the tests should be repeatable, scripted, and reproducible. Imagine that this will be needed to run from end to end with scripts or, for instance, Ansible playbooks, so they can be run automatically. So this slide summarizes the execution flow of challenge one as a end-to-end experimentation pipeline, if you want. The first one, you deploy CODECO in a controlled environment, for example, using a local Kubernetes setup such as Kind. In step two, you define the dynamic stress test scenarios, not static load tests, but scenarios with loads, failures that change over time. In step three, step three focus on execution. So the stress tests are run automatically using scripts or pipelines, so the experiments are repeatable and can be run consistently. Step five, you create a database and then you collect relevant metrics such as throughput, CPU, memory, across throughout the duration of your experiments. And finally, step five, you analyze how CODECO behaves under stress, report your findings, compare with a baseline, and propose improvements based on data, such as identified bottlenecks, for instance. Moving on to challenge two, this focuses on security mechanisms for CODEF. So the end-to-end security posture of a Kubernetes cluster, unlike the first challenge, which idea was to stress the system. Here, the objective is to identify vulnerabilities, propose defenses, and validate those defenses in a measurable way. The first part of the challenge is a threat analysis, so understand where a cluster may be exposed or vulnerable, for instance, to an attack. Here you need to look the architecture, the data flows, the potential risks. For instance, insecurity faults, missing authentication, cryptography, etc. And then you need to design and implement security mechanisms based on those limitations, these issues that you find. For instance, authentication, authorization controls, encryption, security faults, network policies, or hardening practices. So a good idea for this challenge would be to base your solutions on established security frameworks and threat models such as CIS benchmarking, MITRE attacks, NSA Kubernetes hardening guidelines, etc. And once the mechanisms are in place, you need to validate them with security testing. For instance, check their effectiveness on, for instance, how many vulnerabilities were eliminated or mitigated, what's the success rate before versus after, what is the added overhead of the security mechanism that you introduce in terms of latency or resource overhead. Again, the execution flow starts from deploying the Kubernetes cluster. In step 2, you identify the threats and attacks. This includes interfaces, misconfigurations, insecurity faults, etc. In step 3, you define, you design the concrete security improvements based on the identified threats. So here a proposed example is presented in GitLab focusing on RBAC with a set of teams potential in a multi-tenant environment where you need to define the rules, roles, and access rights. So this is an example that we propose to have. Step 4, focus on implementation and validation. For instance, when the security mechanisms are implemented, you need to test them using automated security testing techniques. For instance, static or dynamic analysis, fuzzing, penetration testing, etc. And finally, you measure both the security improvements and their performance impact, if there is one, and report the whole procedure that you followed. And finally, we have the third challenge, which focuses on testing, debugging, and AI-powered assistance. So this focuses on how an experimentation environment like CODEF, the CODECO experimentation framework, is tested, debugged, and maintained, especially under real-world deployment conditions. So this is not about running tests. This is about evaluating test suits, debugging, intelligent assistance tools that can reduce the time to detect and time to fix, and they can improve the quality of experience and quality of life of a developer or an experimenter. Here, participants are expected to define the set of tests, units, integration, regression test, and they should be executed in an automated, repeatable way, of course, as all challenges. So in addition to testing, the challenge explicitly mentions the AI-powered assistance. For example, tools that can help localize bugs, propose fixes, prioritize tests, or check logs more efficiently. Because the learning curve of a Kubernetes thread, of a Kubernetes environment, might be too harsh for a new experimenter. The aim in general is to explore how such intelligent tools can be enhanced, can be used to enhance the quality of experience of developers within experimentation framework. And because this is mentioned as a benchmarking challenge, we not only evaluate whether the tests pass or fail, we also measure their effectiveness in testing, debugging, for instance, using some AI assistance. Again, step 1, you deploy the Kubernetes cluster. Step 2, you define the test scope and the quality goals. For instance, what types of tests you need to run, unit, integration, stress tests, whatever, and what quality metrics you want to improve. Step 3, you need to build or integrate an AI-powered assistant. So this will support developers by helping them with tasks such as bug detection, issue localization, generation, log analysis, or even a report generation, which is interesting when we're talking about an experimentation framework that automates the whole process from end to end. Step 4 focuses on benchmarking, meaning that you measure the effectiveness of what you created and the impact of the assistant on productivity or measuring time to detect, time to fix, metrics like that. And of course, finally, all experiments should be automated, documented, and reported so the results can be evaluated and be reproducibly. Expected outcomes. Of course, all challenges, we expect them to be well documented with the tests, the procedure that we followed, all the specifications you need to define. And of course, you need to have a clear report with results, analysis, and recommendations. And because we're talking about an open source experiment, an open source contribution, the code quality and documentation must be in a good shape in order to be used also by other experimenters and the broader community. And that's it. Thank you very much for your attention. If you have any questions or you need support, please feel free to contact me. And we look forward for your participation in the CODECO RCEP challenges. Bye-bye.
So the concepts and components that I have just presented form the foundation of the CODECO framework and are also important for the innovation and research community engagement program challenges. So the challenges are designed to move beyond the architectural design of CODECO and to demonstrate how CODECO can be used in practice beyond the use cases that have been proposed by the consortium. These challenges invite you to experiment directly with CODECO's orchestration capabilities, focusing on concrete and short time achievable goals. For instance, strategies for energy awareness or resilience, or for security analysis, adaptability, and of deployments across the edge cloud continuum. In particular, we call the attention for the energy awareness strategy challenges that build on PDLC monitoring, also for the challenges that involve the synthetic data generator of CODECO, challenges on secure connectivity, challenges on benchmarking the performance of the scheduler in CODECO, and a lot more. So you will be able to work with real metrics that CODECO captures and to define your own cost functions, to provide and support performance benchmarking approaches and results that are important to our community. So via the challenges, CODECO becomes a hands-on experimentation platform rather than just a framework. Your feedback, your results, your insights, they will contribute directly to validating the CODECO's design choices and help us also in our future directions. So I encourage you to use this overview as a reference while engaging with the challenges and to explore this new approach of orchestration, so the so-called data compute network orchestration, how it can be extended, how it can be used on other domains, how or what would it require to be adapted to other use cases. I leave in this slide some pointers for the main CODECO outputs. These include the CODECO blueprint architecture, open source software toolkits available in the Eclipse GitLab repositories, an experimentation framework, so an emulator called CODEF, created in CODECO, datasets, some basic tooling for AI governance and resilience analysis, training materials, so our CODECO Learning Hub. All of these are made available to help you in engaging with us and also with the challenges. Thank you.